When implementing digital systems, there's a wide range of technologies to choose from, but coarsely they can be divided into 4 types: discrete components, application-specific integrated circuits, configurable logic devices, and processors. Each type has its own advantages as well as disadvantages. In this lecture, we will go through and talk a bit about each of these technologies. Probably the first technology to encounter while learning digital circuits is to implement designs using discrete components. Discrete components come in many flavors. Some are designed for high speed, others are designed for low power consumption. Also, the physical size of the IC package varies a lot, from relatively large to very, very tiny. Discrete components are manufactured as integrated circuits, and each package usually contains 4 to 6 gates of a certain type. For example, the IC 4700 contains 4 2-input NAND gates. However, it is also possible to find ICs which only contains a single gate or flip-flop. The speed of a gate is commonly given in datasheets as the propagation delay. This is the time it takes for the gate to change its output after a change of input. So with a chain of connected gates, it is possible to calculate the total propagation delay of a circuit by adding delays of individual gates. Now imagine that you have designed a counter by implementing a final state machine. It consists of flip-flops as well as a combinational circuit which generate the next state. How fast could you run this circuit? That is, what is the maximum clock speed you can use for the flip-flops? Well, let's assume that our flip-flops change value on the positive clock edge. The outputs of the flip-flops act as input to our combinational circuits. At the positive clock edge, flip-flops change value. For our circuit to operate properly, the combinational circuit must generate logic values for the next state before the next positive clock edge. That is, the inputs must propagate through the combinational circuits before the next rising clock edge. To determine the maximum clock speed, we calculate the worst case propagation delay. Let's assume that all gates have the same propagation delay of 10 nanoseconds. In this example, the bottom branch gives our worst case delay since it has a chain of 4 gates. Thus the worst case propagation delay is 14 nanoseconds. So if we ignore propagation delays of the flip-flops, we would be able to run this circuit at 25 MHz. However, some assumptions were made in the previous calculation. It might be that the input pattern that generates the worst case delay might not be a valid state code, and thus this input will never exist. Also, the input to the flip-flops must be stable a certain time before the rising edge, otherwise the flip-flops might not work properly. The propagation delay of a gate is also dependent on what's connected to its output. Connecting a high number of gates to an output will increase the propagation delay of the driving gate. The bottom line is that when designing larger systems, it becomes very hard to do these kind of calculations by hand. Thus, one makes use of electronic automation tools to handle this. Another practical thing to consider when using discrete components is that there exist many standards of what voltage level corresponds to a logic high and a logic low. For example, if you were to buy a NAND gate from Texas Instruments, you would be able to get it in 5 different voltage flavors, where one defines a logic high as a value between 2 and 5 volt, and another defines it as 1.7 to 2.7 volt. Okay, let us take a look at the next kind of technology that can be used to implement digital circuits, the Application-Specific Integrated Circuit, or ASIC. With this technology, you implement the logic within an integrated circuit by connecting transistors such that they implement a certain logic function, for example a NAND gate. Many gates or flip-flops are then connected inside the IC to implement a complete circuit. This gives relatively short connection wires in comparison to implementations with discrete components, where the connections are done outside the IC. Short connection wires are good since they generally lower the capacitive load at the output of gates and thereby decreases the propagation delay as well as the power consumption. When designing ASICs, you can do it in different ways. You could do a full custom ASIC, where you can control the size of each individual transistor to suit your needs. This can of course be very time consuming and require a lot of simulations to verify the functionality. The next step is to do a standard cell ASIC. You then use predefined transistor structures from a library that implement different logic gates. These libraries are created by IC manufacturers and has been tested such that they can be manufactured. However, designing ASICs is a complex task which requires both a lot of knowledge as well as good automation and simulation tools. On top of that, you need a lot of money, as the manufacturing of ASICs is very expensive and for most cases only suitable for mass production. And once the IC has been manufactured, it is not possible to change it. So if some error is found in the design after manufacturing, a new IC must be manufactured, which will cost a lot. To implement digital designs, you can also use a configurable logic device. You buy this device as an integrated circuit, and inside the package, the manufacturer has put logic blocks which can be configured by programming the device. This device also has a matrix of wires on the chip, where the designer can program how wires should be connected to each other as well as to logic blocks. One of the earlier versions of this device was the Programmable Logic Device, or PLD. It consisted of one layer of AND gates and one layer of OR gates. The designer programmed how inputs should be connected to the layer of AND gates and how the outputs of the AND gates should be connected to the OR gates. Thus it was easy to directly implement logic functions written in disjunctive normal form. Later on came the Complex Programmable Logic Device, or CPLD. Basically, it was an extension of the PLD, where manufacturers included flip-flops in the IC, such that it was possible to implement finite state machines in a single IC. The CPLD also contained a larger number of gates compared to the PLD. In the latest step of evolution in these kind of devices is the Field Programmable Gate Array, or FPGA. The main difference between the FPGA and its successors is that the logic is implemented by lookup tables or truth tables instead of gates. The designer can then program the content in the lookup table such that it implements a certain logic function. FPGAs typically also contains a lot of other hardware like adders, multiplexers, AD converters, Ethernet interface, memory blocks and so on. And all the wiring inside the FPGA is controlled by the designer through programming. The designer also decides which wires that should be connected externally to the pins of the IC package. This is an example of how lookup tables can be used to implement logic functions. Let's assume that our logic function has three inputs, A, B and C. Now to implement this function, we simply write the value of Q in each row. To implement this function in an FPGA, we program the column Q into a lookup table and also instruct the FPGA to connect A, B and C as inputs to the lookup table. Now the three signals A, B and C will control which row in the lookup table that will be used to assign Q a value. There are two major manufacturers of FPGAs, Xilinx and Altera, where the latter was recently acquired by Intel. We will now take a closer look inside the FPGA from Xilinx. Other vendors have similar content inside their FPGA, but they might have different names for their content. As an example, we will take a look at the Arctic 7A200T, which is one of Xilinx's mid-range FPGAs. It contains an AD converter, PCI Express interface, gigabit transceivers, PLL for scaling the clock frequency, special hardware for digital signal processing, 13 megabit memory, and has around 500 input-output pins, which can be connected to other parts of a system. This FPGA contains around 15,000 configurable logic blocks, or CLB, which is where you implement your logic functions. Each configurable logic block contains 8 6-input lookup tables and 8 flip-flops. Other vendors might call these blocks different things. Lastly, it is also possible to implement some digital system in ordinary software by writing a program, which is then executed by the processor or a more specialized digital signal processor. However, every execution step is controlled by the system clock, and thus it is not possible to implement combinational circuits. The benefit of using a processor is that it is quite easy and quick to implement, for example, a finite state machine in a high-level programming language. But it might be hard to control the timing of signals, as the number of clock cycles needed to execute a single line of high-level code may variate. If we compare the three technologies, ASIC, FPGA and processor, we see that the processor is most flexible, since we can change the design by running another program, whereas the ASIC is the least flexible, as it requires a remanufacturing if we would like to make any changes. But if we take a look at other aspects like power consumption, speed, physical size, we see that ASICs have the highest performance and processors the lowest. When it comes to cost, ASICs are really expensive and processors are cheap. FPGAs comes in the middle of all these metrics. It is rather cheap, has quite good performance, and is pretty flexible as it can be reconfigured. And in many cases, FPGAs are used to make prototypes before ASICs are sent for manufacturing. Last, I would just like to point out that implementing designs as ASICs or on FPGA is rather complex tasks. Luckily, there is electronic design automation tools that help us implementing digital designs, and in the following lecture we will take a closer look at one of these tools.